In section 1.6, we're going to take a look at graphing quadratic functions. So if I've got a quadratic function, meaning my standard form looks like this, ax squared plus bx plus c. Notice, by the way, that the highest power in my function is this exponent of 2. That's what makes it quadratic, right? It's quadratic if it's got an x squared as its highest power. All right, we're going to start with the simplest possible quadratic function, just f of x equals 1x squared. And I'd like to sketch this particular one by hand. I don't think it'll take us too much. I'm going to choose x values running from -3 to +3. And since the y value is just the square of the x value, -3 squared would be 9. -2 squared is 4, and so on. Just squaring all those x values. All right, let's graph our function. -3,9 is my first point. I'm just going to plot that, and continue on to -2, 4, and again, so on. Just graphing all the points from this table. And what I see is this kind of a U-shaped thing happening here. Keeps on going up forever on both ends. That graph has got a name. It's called a parabola. And the graph of any quadratic function will turn out to be a parabola. It will be that basic shape with some variations that we're going to talk about. All right, as far as what's really important on that parabola, notice that our parabola is going to have a turning point. In this case, it's a local minimum, right here at 0, 0. That turning point is called the vertex of the parabola. And so in our case, that vertex or turning point is that origin, 0, 0. The parabola also has symmetry. If you imagine, in this case, kind of like a mirror sitting here on the y-axis, the two sides of the parabola are really just a reflection of one another across the y-axis. So we say the axis of symmetry is that y-axis. It's the mirror line for the parabola. So the axis of symmetry here is the y-axis, which would have equation x equals 0. All right, we're going to do a little bit of exploring. If you're doing activity 1.6a, it would be a good time to take a break and do that. But I'm going to do a little summarizing of that activity as well by taking a look at some Desmos graphs so that we're ready to fill in the chart on the next page. So here we go. Here are my graph of y equals x squared, which I've already created in Desmos. Sorry, let me get my volume down here for us so we don't keep on hearing that. There we go. All right, so again, here is the graph in Desmos. Y equals x squared. I'm going to add some other graphs to that. And the first thing I'm going to do is just see what happens if I put a negative sign in front of it. And what you notice, of course, is that you get a reflection across the x-axis. It just flipped the graph upside down, or reflected it across the x-axis. That was really multiplying by -1. What if I multiply x squared by other numbers? Maybe 2x squared. My graph seems to have gotten narrower. What if I do 5x squared? There we go, it's gotten narrower yet. If I multiply by a number smaller than 1, say 1/3, now notice it's wider than the original graph. So these multipliers, seem to simply be changing the width or narrowness or width of our original parabola. I'm going to go back to our notes and summarize what we've seen so far. So here we go. In this chart, we're going to talk about how our original parabola was affected by transformations of graphs, slight changes to the original parent function, y equals x squared. We saw that when we multiplied it by a -1, it turned upside down. The more formal math way of saying that is, it was reflected across the x-axis. So our parabola looked like this. Upside down U now. We also saw that when we put a multiplier in front of the x squared, when the multiplier was greater than 1, the parabola got narrower. And when the multiplier was less than 1, it got wider. All right, the next thing we're going to look at, and I'm going to go back to Desmos to do this, is what happens if I have a number inside the parentheses being added to the x or subtracted from the x. This, by the way, shouldn't be there. I don't know why that's there. We'll get rid of it. All right, so let's go ahead, and again, I'm going to look back at Desmos for a moment, and let's try a couple of those graphs. I'm going to get rid of these. We don't need them anymore. There we go. All right, what if I graph y equals x plus 2 squared? Change the color on that. There we go. You can see that compared to the original parabola, this has been moved to the left 2 units. My vertex is now at -2 instead of 0. What if I try y is equal to x minus 4 squared? Here's our new graph over here. And now you can see, again, here's the vertex. Instead of 0, 0, we've now moved to the right by 4 units. Our vertex is now at 4, 0. So, when I added something inside the parentheses, the parabola moved left. When I subtracted, it moved right. I'm going to jot that down. When I add inside the parentheses, we shift to the left by however many units that number told us, so h units. And when I subtracted, we shifted to the right, h units. All right, the last two things in our little chart here. What if I'm adding or subtracting a value outside of the parentheses? I'm squaring the x first and then adding or subtracting. Let's take a look again at our Desmos graphs. Done with those. And this time, let's try y equals x squared plus 3. Our graph seems to have gone up this time. And then y equals x squared minus 5. And here our graph's gone down by 5 units. Notice the vertex is exactly 5 lower than it was originally when it was at the origin. So when I added, it went up. When I subtracted, it went down. F of x equals x squared plus k. We're shifting up. K units. And x squared minus k, we're shifting down. K units. So, what this tells us is that if we have a quadratic function in vertex form, looks like this, we can actually figure out where the vertex is going to be using transformations of graphs. What's inside the parentheses tells us how far left or right to move, and what's outside the parentheses tells us how far up or down to move. Additionally, if we would like to find zeros or x-intercepts, we can do that simply by setting y equal to 0. Typically, the square root method is going to be the easiest way for us to solve those equations. And then the y-intercept we get by setting x equal to 0. Notice, here it is again, we've seen this before, but x-intercepts are always y equal to 0. Y-intercepts are x equals 0. It's always the opposite variable that you set equal to 0. Last little note before we try a few practice problems. When you are graphing a parabola, you should always plot at least 2 points in addition to the vertex. That gives you enough points to draw a reasonably accurate graph of your parabola. All right, let me pause there and we'll do a couple of examples in the next video.